Hello and welcome to Fun with Physics with Uncle Bob. This week we'll be discussing the Brachistochrone of a rolling object. This would be a companion video to my last one, Brachistochrone with friction and drag. Here we got the rolling object rolling downhill, our slope or path right here. The forces on it should be explained somewhat. The mg gravitational force here, its two components, the parallel component being the driving force of this object. Also a centrifugal force up here because we'll be looking at a curved optimized solution, and its reactive force, centripetal force here, along with a reactive force from this component of the gravitational force. That's explained right here. In addition, we've got a static frictional force acting right here, causing rotation or torque on the object. We've got two other retarding forces, a rolling friction force here and an air drag force here. Rolling friction can be somewhat complicated, but generally it will act in a direction about right here, going pretty close to the center or centroid of an object. We're only interested in the retarding component of this rolling friction force going this way, which I've got right here. In addition, we've got a bearing torque right here acting counter to our main torque from the frictional force right here. So this would be a retarding torque. It's important to note that this torque or force from the bearing is internal and it is not an external force, so that's treated somewhat differently in the equations, which you're about to see. I'll move this on down, so feel free to pause. Again, I wrote this to allow rolling only, no slipping or sliding. Moving on down. Those are the equations. We'll go on to the actual program I wrote in Power Basic. This is the program I wrote in Power Basic using successive approximations through a randomized perturbation of the initial straight line slope. The user inputs are explained and are in this area right here. I'll move this on up and you can pause as you wish. That's the end of page 1. Here comes page 2. I'll move it on up. End of program. Next, we'll go on to look at this program run on screen. Here's the same program on screen. Again, we're going to use a randomized successive approximation method. What I've got are input parameters here from an actual experiment I ran using a large marble rolling down a piece of cardboard. That's all it was. And in this, I did the straight line time for it only. I did not make a curved path to test the optimized solution. But you will see that when I run it. What you're going to see on the output plot coming up when I start this will be the initial straight line going from upper left to lower right. That would be the slope or path of the object. Below that, you'll see the program filling in successive approximation dark lines, so many that it will appear to be just a solid black area, but you'll see that solid black area moving down as it gets closer and closer to the optimized solution. Shortly after it stabilizes to a solution, you'll see below that, just for interest's sake, a blue cycloid curve. I'll run it now. So you see at the top, this is the initial straight line. The program's finding better and better solutions. It's starting to stabilize. Stabilized about now, and you'll see a blue cycloid coming up soon. Here it is, just for comparison. Minimize that, and we'll see the actual numerical output, a straight line time of 1.26 seconds, the optimized time, which would be the bottom of that black area under there that you just saw, 0.702 seconds, a good improvement. It's important to note in this program that sliding or slipping along this curve is not allowed. I wrote it to allow only output and parameters for a rolling object. That's all for now. We'll see you next time.